Okay, good morning everybody. Today we're gonna do a section on logarithms. Okay, that makes sense. Last time we did exponential. Now we're gonna do logs. These topics typically go together. So let's jump right in and start in on the warm-up problem. So does anybody want to help me with warm-up problem A? Yeah, Yasmin?
You would just do 100 would be your penal, and then you would do it times 1.07 to the power.
Yes, perfect. Okay, so we have a population of bacteria which begins with 110 bacteria. Okay, and what Yasmin said is that begins with 110 bacteria. That's telling us that P naught, or P null, as she said, is going to be 110. Okay, so that's our initial thing. And remember here, we're looking for a formula which looks like P of t equals P naught times A to the power t. Whoa, what have I done there? A to the power t. Oh, I see. It's because I'm writing up there. A to the power t. Just imagine that t is in the power. A to the power t. Okay. So we found P naught, and how did we figure out what A was going to be? We looked at this percentage here. Okay, so 7%. Is that going to be my A, Yasmin?
No, you have to add it. You have to do 1 plus 0.07.
Exactly. This is R. This is telling me R is equal to 0.07, which means that A should be 1 plus 0.07, which means that A is going to be 1.07. Okay, so we get P of t equals 110 times A, that's 1.07, to the power t. Sweet. Any questions about problem A? Does everybody kind of agree with the process we took here? Okay. Let's do problem B. Gary deposits $2,500 into an account that pays 3% interest annually. Okay, 3% interest annually means each year I earn 3% interest on what I had at the start of the year. So how much money will we have after 10 years? Okay, so first of all, we're going to have to find our equation. We're going to do it the exact same way we did before. 2,500, that's going to be our original amount. That's P naught. 3%, that's R, 0.03. So A is going to be 1.03. So P of t equals 2,500 times 1.03 to the power t. And if we want to find out how much money we're going to have after 10 years, what should we do?
Plug in 10 for the t.
Yeah, plug in 10 for t. So we're going to do P of 10, and that's going to be equal to 2,500 times 1.03 to the power 10. Let's check. Use my calculator today. Gotta go sideways for this one. All right, 1.03 to the power 10. Multiply that by 2,500. We're gonna have 3,359.79. So if you can invest in some kind of stock or index fund or Roth or whatever, and or maybe a CD, well, probably you wouldn't get such a good interest rate on a CD, but if you could invest in something like that, it'd be a pretty good investment, right? Because 10 years we made $859 just by sitting there and doing nothing. Okay, so that's the power of compound interest. It's really good. All right, any questions about how we did problem B? Seems pretty straightforward, I think. All right, let's talk about logs. Okay, so as I said, logs and exponentials go together. Okay, so when I say natural logarithm of x, what I mean is the number C such that e to the x, e to the c is equal to x. Okay? So, this equation here is the corresponding exponential equation to the logarithmic equation c equals ln of x. Okay, so we have these two equations, all right? Okay, so what I want to say that's really important about the logarithm is that, what is that letter? ln of x and e to the x are two functions which have a very special relationship. Can anybody tell me what the relationship is? Yeah, Yasmin? They're inverses. Can you tell me what that means?
Like when you graph them, they look opposite.
That's true. When you graph them, they look opposite.
The x and y values are flipped.
X and y values are flipped. Good. And in particular, they undo one another. ln of e to the x, so if we plug one of these functions into the other one, what are we going to get? Not 1. You're on the right track, though. Anybody? What are we going to get if we... Yeah?
0.
Not 0. If I start with x and I do something to it and then I undo that thing, what do I get back? X again. Okay. And what about e to the power ln of x? Then I'm going to get x. Okay. This is the definition of what it means to be an inverse. If I plug one into the other, I get back my original thing. Okay, so let me draw really quickly what's going on here. Add a page. So remember, oh, let's not have that paper. Yeah, we want the blank paper. All right, so remember we talked about these functions as being kind of like conveyor belts, right? So what I mean when I say that these are inverses is, let's say this is the E machine. And this is going to be the log machine. So if I send some number x into the E machine, what pops out the other side is the number e to the power x. Okay, so x is just some number, which I could choose any number I want, maybe 10, 20, -10, something like that. And I plug it into the E machine, and what pops out is e to the x. If I plug something which looks like e to the x into the log machine, then I get back the original number. Okay, so 10 goes in to the E machine, e to the power 10 comes out. If I plug e to the power 10 into the log machine, it's just going to undo the process that the E machine did. Okay, likewise, if we flip-flop these guys, then it would be x going into this thing. If it was log, then it would come out as ln of x, and then go into E, come back out as x. Okay, so these machines undo whatever process the original one did. Okay, all right. So let's complete the following statements. Okay, this is exciting. So if y is equal to ln of 100, then blank to the power y is equal to 100. Who can fill in my blank? These are the corresponding equations. We have the logarithmic equation and we have the exponential equation, and they're related by this rule which we wrote down here in the logarithm box. So if y is going to be equal to ln of 100, then what should go in this blank? Just a guess is fine. Not ln. ln's on the left side. So we have the logarithmic equation here. So this equation should be exponential in nature. That's right. It should be e to the y here. Okay. This is the corresponding equations. Okay. So this one here is this one here. And this yellow one here is this one here. We just wrote it with different letters. Okay. Wrote it with different letters. Okay, so you see how when we had, maybe highlight with red, when we had x here on the inside, x shows up in the exponential equation on the other side of the equation. So when we had 100 on the inside here, we had 100 on the other side of the equation. In here, which I'll circle with pink, this c here was alone in the logarithmic equation. In the exponential equation, it's the exponent. Y became the exponent. Okay, so we're going to flip-flop all the time between these different forms of the same equation. Okay, these two equations in yellow and red say the same thing. They both define what y should be. And they define y to be the same number. Okay? All right. ln 5.5 is the power of blank that gives blank. Okay, let's try to do that one together. So we have ln of 5.5 equals x. Who can tell me what's the corresponding exponential equation? Yasmin? Yeah, e to the x equals 5.5. Okay, so if ln 5.5 is equal to x, then ln 5.5 is the power of blank that gives blank. Well, x is a power on what constant? E. Power of e that gives, by gives I mean e to the x is equal to 5.5. Okay, who can help me with C? ln of blank is the power of blank that gives 500. Take a second to think about it. We'll see if we have any volunteers. All right, anybody want to go? Sam?
ln 500 is the power of e that gives 500.
That's exactly right. Okay. All right, if e to the m equals n, then ln of n should be equal to what?
X.
Not x. We don't have an x in this equation. Here we've got m and n, right? So the corresponding logarithmic equation, if we applied the natural log to both sides, on the right side we get ln of n, and on the left side ln's going to cancel the e, and what's left over? M. Okay, so we're playing a little bit fast and loose with the constants. Okay, sometimes we're going to be talking about y equals e to the x, or we'll be talking about e to the m equals n, or all sorts of different constants, but just remember they're just a placeholder for what might be a number. Okay, just a placeholder. All right, let's do problem number 2. Rewrite the following using exponents instead of logs. Okay, so I have ln of 5 is equal to 1.609. Okay, so they gave me the yellow equation up on my logarithm box. We have the yellow equation, And we're supposed to write the blue one. Okay? So, the way I'm going to do it is, I know that whatever's inside the parentheses here, okay, whatever's inside the parentheses here is my x, so to speak, in my yellow equation. Okay? When I raise both sides of this equation to be the power of e, we're going to get just 5 on this side because e and ln undo one another. And on the right-hand side, I'm going to have e to the power 1.609. Okay. Part B, ln of 1 equals 0. Okay, we can do this one a little bit faster. We just did one. We know that 1 should be by itself, and this should be equal to e to the power 0. Is this a true statement? 1 equals e to the power 0? Yeah, that's a true statement. Any number, if I take a number to the power 0, is 1. 1 million to the power 0 is 1. Negative 1 to the power 0 is 1. Okay? Alright. How about ln of a equals b? Well, that's just going to be the same thing again. A equals e to the power b. Okay? Alright. We can do problem 3 real quick. Now we want to go the other way. We want to start with our blue equation, and we want to write the yellow one. Okay? So, you'll start to notice that when we switch between these two forms, the number that was originally by itself is now going to be tied up with the opposing function. Okay? So when we have this number by itself, it's now going to be tied up with the opposite function. So we're going to apply ln to both sides. The ln and the e are going to cancel one another. We're going to get just 15 on this side. And that's going to be approximately equal to ln of this huge number, 017.373. Okay? By the way, notice that when I'm given an approximately equal to sign, that's what this sign means, is approximately equal to. I have to stick with that sign, okay? It would be bad form, so to speak, if I were to write an equal sign after being given an approximately equal to sign. Okay, let's do the next one. E to the t equals h. We're flying through these now. This is going to be t equals e to the power h. Okay, let me stop and ask.
Wait, were we supposed to write that one as a log?
Oh, excuse me, yeah. What am I doing? Guess that's what happens when you try to fly. You gotta walk before you can fly. We should do t equals ln of h. Thanks for pointing that out. Okay. Are there any questions on these first 3 problems? Is this review for some people? Okay, sort of. All right. Well, if you haven't seen it before, it's no problem. Just make sure you get these definitions down, and then we'll be using them for very often for the rest of the class. Okay, let's talk about the properties of logarithms. Okay. So anybody who has seen logs before, would you like to give me a property of the log? Is it vaguely coming back that there are some important properties involving adding and multiplying and taking powers of things with logs? Is vaguely ringing some bells? Okay, we'll go through them together, and then we'll practice together using them. Okay. So the first important property is that ln of a times b is going to be equal to ln of a plus ln of b. Okay? So if we see something that looks like the left-hand side, we can replace it by the right-hand side. If we see something that looks like the right-hand side, we can replace it by the left-hand side. Sometimes problems will ask us to split up logs or take separate logs and put them together. Okay? The next important one is ln of a divided by b. that's going to be equal to ln of A minus ln of B. Okay, so multiplication inside corresponds to addition outside. Division inside corresponds to subtraction outside. Okay? I always find this easy to remember because the subtraction sign here, that's not what I want. The subtraction sign here looks kind of like if we just tilted this division sign here. Okay, so that's one way you can remember it. All right. Next important property. This is the most important property of logs. ln of A to the power P is equal to P times ln of A. Okay? This, by the way, this comes from the first property. If we have A to the power P, that means we're doing A times A times A times A P times, which means that outside the logs, we would add up ln of A P times. So that's how we get this P times ln A here. Okay. Next two important properties, we have ln of e to the x equals x. We already covered that one. E to the ln of x equals x. We already covered that one. And ln of 1 equals 0. We also did that in an example problem, I think. Okay. So I'll let you guys write all that down for a second. Then we'll move on to problem 4. Is it okay for me to scroll down now? Okay. So now we're going to evaluate the following without using a calculator. Okay, e to the power ln of 17. We've got e and ln together. What are we thinking about that? Remember, e and ln are inverses, so if we see e to the power ln, what do we think is going to happen?
It would just be 17.
Yeah, they're going to undo one another, and we're just going to get 17 back. Okay, this is the situation where we put it in the e machine. Actually, this is the situation where we put it in the ln machine first, and then we put whatever came out of that into the e machine, and then they're going to undo one another. All right, how about b? Who can do b for me? ln of e to the power 3. Yasmin? Yeah, just going to be 3. All right, this one's tricky. ln of 1 over the square root of e. It would be convenient if I could express the inside of this function as a power. Can I write this as ln of e to the power blank? My question is, what should go right here? Anyone besides Yasmin? Alice, you want to give it a shot?
To the negative 1/2.
That's exactly right. To the negative 1/2. Okay, the 1/2 comes from the square root. Okay, we know if we take a square root of a number, that's the same as taking that number to the 1/2 power. We also know that x to the negative a is equal to 1 over x to the a. So if we see 1 over x to the a, we can write it as x to the negative a. Okay, so this is just going to be e to the negative 1/2. Okay, so now I'm doing ln of e to some power, and now it looks kind of like how the first problem looks, or the second problem, right? We have ln of e to some power. So we know that these two things are just going to undo each other, and we're going to be left with negative 1/2. Okay. Thank you, Alice. Any questions about this kind of inverse property of exponential functions and logs? Okay. All right, we want to rewrite all of these guys using our log rules. So we're starting with something which is all together on the inside, and we're going to try to use these properties here in pink. to split them up. Okay, we got to split them up. So I'm just going to proceed somewhat arbitrarily. I'll start by saying, okay, well, I'll split up the numerator and the denominator first. Okay? If I have log of a over b, I can express that as log of a minus log of b. So I'm going to split up my numerator and my denominator first. So I'm going to write equals ln of 3x squared, and then I should have a minus sign, and I'm going to write my denominator now, ln of yz. Now let's focus on splitting up ln of 3x squared equals ln of 3 times ln of x squared minus ln of yz. And I gotta have more forethought in terms of the space I'm leaving myself here. Okay. So what I did here was, since I have 3 times x squared, I used the rule that if I have a times b, then I get ln of a plus ln of b. Alright, now I'm going to use the power rule on the x squared. Ln of 3 plus, the power comes down front, 2 ln of x minus ln of yz. And now I have one thing left to do, and that's to split up the yz. Okay? Now, when I do that, I'm going to leave this part the same. Minus, and what I'm going to do here is I'm going to be very careful. Since I'm subtracting all of ln of yz, I'm going to put parentheses here because I need to remember to distribute this minus sign, okay? What's going to go on the inside of these parentheses should just be ln of yz, okay? So ln of yz, that's what's going in here. And the way that I'm going to split it up is using my multiplication rule. So ln of a times b should be ln of a plus ln of b. So I'm going to get ln of y plus ln of z. Okay, so my final answer is going to be ln of 3 plus 2 ln of x minus ln of y minus ln of z, because I distributed the minus sign. Okay? You feel okay about that problem? Any questions? That's kind of like a big first problem to put all those rules all together, but was any part of that confusing? I think some students might find it confusing where to start. I started by splitting up the numerator and the denominator. You don't have to do it that way. If I wanted to, I could have started by splitting this up as, say, ln of 3 over y times x squared over z. I could have split it up like that and then used the multiplication rule to split it up as a sum. Okay, so there's not just one way to do this problem. Okay, so however you want to split it up first, you can do it that way. I think it's kind of natural to split it up on the numerator and the denominator first, because then we get 2 logs, which are a little bit more manageable, I think. I don't like fractions, so I like to get rid of the fractions as soon as I can. All right, that's that problem. 11. I got to make sure I keep enough time for this part. Do we have time? Okay, I'll leave B as an exercise for you guys. You guys can try it on your own later. We're going to do this one. So now we're going to go the opposite direction, okay? We start with a bunch of logs, and we want to put them together. Okay. The first thing that I want to recognize here, okay, is that my rules, which I've written up here, when I have the right-hand side looking like this, we have no numbers being multiplied in front, okay? We don't have constants here, okay? If we want to take this equation down here and put it into that form, the first thing we have to do is get rid of these constants here if we want to apply those rules. Because the rules say you can do this when there's no constant. Right now in our problem we see there are constants, so we got to get rid of those first before we can do our summing and subtracting rules, okay? How can I get rid of this 2 out front of the ln b? Okay, let's focus on this part first. I want to write this as ln of something. Is there a rule that I can use if I'm multiplying out front? Ellie?
Is it ln of b squared?
That's right, b squared. We just moved it in as a power, okay? If we take a power, move it out, we can move it back in. Plus ln of, what happens to 3 and c? C to the 3. And the last one, we're going to get minus ln of d to the power 4. Okay, now we've got ln's and ln's with no constants, so we can go ahead and apply the rules about summing and subtracting. Let's do the first one first. Ln of a minus ln of b squared is going to be ln of a over b squared. Plus, let's combine the next two. We did these two, and then we'll do these two. The next one's going to be ln of c cubed divided by d to the power 4. And now I want to combine these two. It's a sum, so we're going to multiply those guys instead of adding. Okay. So we get ln of ac cubed over b squared d to the 4th. All right. That's how we can take logs that are all split up and write them as a single log. Okay. So these are just exercises to get you familiar with these rules, okay? When we're doing calculus problems, there are times where it's going to be much more convenient to work with a single log. There are also times where it's going to be far more convenient to split everything up, okay? It's just going to depend on the circumstances of the problem that we're working on, okay? Whether we're integrating or we're taking derivatives or we're trying to manipulate the equation algebraically. We need to be familiar with these rules so that we can use them to solve problems later on. Okay, any questions about these two problems, about the log rules? Okay, like I said, I think these extra other two problems can be good practice for you guys. I think it's a bit redundant to use class time for them, and I want to make it to this part about solving equations using logarithms. Okay. Okay, so if we're given an equation where we don't know the exponent, such as this problem A here, problem 7A, where we don't know the exponent, okay, we can figure out what it is by using logs, okay? So these equations are typically pretty nasty to solve, but we've just learned this powerful tool, which is going to allow us to bring these powers down using the very special rule, which I starred up here, okay? ln of a to the power p equals p times ln of a. That's where the magic is going to happen, okay? That's where the magic is going to happen. So if I have an equation, if I have an exponential equation with unknown exponent, say for example 3 to the power t equals 10, one can apply the natural log to both sides to get. Okay, when I say apply the natural log to both sides, I mean exactly what I mean, okay? So if I am manipulating an algebraic expression with an equal sign, I know that if I do something to the left-hand side, such as multiplying by a number, I have to do it to the right-hand side too in order to maintain our equation. Yes?
Can you just like read it again?
Oh, my handwriting's pretty bad, huh? Okay, what this says is, I'll highlight as I go. If I have an exponential equation with unknown exponent, say, for example, 3 to the power t equals 10, one can apply the natural log to both sides to get ln of 3 to the power t equals ln of 10. Okay? Now, the magic is going to happen on the left-hand side. I have ln of 3 to some power. I can bring the power down front. So this is the same as saying t times ln of 3 equals ln of 10. Okay? Now, if I just want to isolate t, I can do it quite easily by recognizing ln of 10 and ln of 3 are numbers, okay? If I type in on my calculator ln of 3, it's going to return to me some number, okay? So when I see ln 3, I can treat it as a number, okay? So I can treat this equation the same way that I might treat some equation like 6t equals 12. What I would do here is I would just see, aha, I have a number times t equals a number. I'm going to divide by the number with t. So I just divide by 6, right, on both sides, and I would get t equals 2, okay? I'm going to do the exact same process here, and the way that I know that I can do that is because ln of 3 and ln of 10 are constants. They're numbers, just like 6 and 12 are numbers, okay? So what I'm going to do is just divide both sides by ln of 3, and this is going to give me t equals ln of 10 divided by ln of 3. Okay? I could do that on my calculator. Just take those two numbers and divide. All right? A lot of students get tripped up and think that we can't do this because ln is a function. Yes, ln is a function, but what's inside of the function is a number. And if we plug a number into a function, we get another number back. Okay? So ln, in this context, ln of 3 represents a number. I just want to really drive that home. Okay. So let's try some of these problems. We got about 10 minutes left of class, so we might even have time to go back and do some extra problems. All right, 3 to the x equals 29. I'm just going to apply the log to both sides. ln of 3 to the power x equals equals ln of 29. I don't know where that came from. Okay. Now I use the power rule on the left-hand side. X times ln of 3 equals ln of 29. Wow, this is just like the problem we did in the last thing. Okay, now I have a x times a number equals a number. The way I would solve that in high school algebra is by dividing by the number on the left-hand side. So I divide both sides by ln of 3. On this side, I can cancel it. Divide by ln of 3 on that side. That tells me that x is equal to ln of 29 over ln of 3. And if you want to, you could plug that into your calculator and figure out what that number is. It's going to be some nasty decimal. All right, sweet. Let's do this next one. My unknown is in the exponent. That's my cue. Apply the log so that you can bring that down. Okay? So, ln of 5e to the 2x equals ln of 30. Okay, now I have to be careful with this left-hand side here. Okay, it's going to be tempting to try to just bring this guy down front. Okay, it's going to be tempting to just automatically bring that guy down front. There's something else we have to do first. Can somebody tell me why it would be incorrect? Why it would be incorrect to write this is equal to 2x times ln of 5e.
For the x isn't a constant.
The x is in the power, so when we, okay, sorry, this is confusing. What I shouldn't have written this x here. What I meant to say was like, this is not right. Don't do this. So why is this not equal to this?
Because then 5 and e would have to be in parentheses.
Yes, exactly. Okay, this would be true if we had parentheses here. But the power 2x is only being applied to the number e. Okay? If we had 5e to the 2x like this, then that means 5 to the 2x times e to the 2x. Okay? That's what this means. We don't have that. We have 5 times the number e to the 2x. Okay? And this is very different. Okay? So 5 is not being taken to this exponent, so we can't write that. What should we do first to remedy this situation? We can't use the power rule straight away. Yasmin?
You can use the addition rule.
Exactly. I'm going to use the addition rule for multiplication. I have 5 times e to the 2x. I'm going to write this as ln of 5 plus ln of e to the 2x equals ln of 30. Okay, now I can use the power rule, but just on this one. Okay, now I get ln of 5 plus 2x ln of e equals ln of 30. What's ln of e? Can anyone tell me what that is? If I plug e into the ln function, x, that would be if I plugged in e to the power x. Yeah, it's going to be 1. The power here on e is kind of tricky because we don't usually write it, but the power here is really 1. Okay, I just wrote, let me draw your attention, I wrote that right there, okay? This is e to the power 1. So if I do ln of e to some power, that will return to me the power. So this whole thing in brown is actually equal to 1. So this just looks like 2x times 1. So I can rewrite this as ln of 5 plus 2x equals ln of 30. I'm going to move the ln 5 over to the other side. We're going to get 2x equals ln of 30 minus ln of 5. Ooh, this is a good example. So there's something convenient that we could do here on the right-hand side? Yeah, Ryan? Yeah, we can combine these two logs on the right-hand side using division. So this means 2x is equal to ln of 30 divided by 5. So 2x is equal to ln of 6. And now we want to get x by itself. Well, we can just divide both sides by 2. We get x equals ln of 6 over 2. Okay, so that was that problem. All right, a little bit more complicated of a problem. All right. The crucial information that this problem teaches us about logs is that if we have a power inside of a log and we want to bring it down, we have to make sure that that power applies to the entire preceding number, by which I'm referring to this yellow highlighted part here. Okay? In our case, the power was only applying to e. Okay? So I think Alice told us that if we had had parentheses on the 5e, meaning that that entire thing was taken to the power 2x, then we could have brought it down. Okay? But since that wasn't the case, we had to split it up first. Okay. Are there any questions about problem A and problem B and how we're using these logarithms to figure out these unknown exponents? Okay, not too bad so far, I guess. All right. We'll do one last problem. We'll do this one here, which looks kind of like the interest, right? This looks like an interest problem. This looks like I put $200 in the bank and I earned 3% interest for X years, and then I had $500. That's how we should read this problem. Okay? The way we're going to solve it, same way we've been solving it before. ln of 500 equals ln of 200 times 1.03 to the power x. Now, be careful because the power x is only on 1.03, so we have to split up this log first before we can bring it down. ln of 500 equals ln of 200 plus ln of 1.03 to the power x. So subtract the ln of 200 over, we'll get ln of 500 equal minus ln of 200 equals, now I'm going to apply the power rule to this guy, x times ln of 1.03. Okay? The left-hand side I can combine. It's going to become ln of 5 halves equals x times ln times 1.03. I did that because I combined these two subtracting logs as a division on the inside. 500 divided by 200 is 5 over 2. Now I divide both sides by ln of 1.3 and I get x equals ln of 5 halves divided by ln of 1.03. Okay? To be really nice, we should probably write this all as a decimal. So we'll write ln of 2.5 over ln of 1.03. Okay, so that's how we solve that problem. Okay, that's all we have for today. If you have questions, then please come to my office hours today. They're from 11 to 1. You can find the link to connect to the virtual office hour room on Blackboard under course content. A lot of people wrote on their exit slips things that said something like, I wanted to see more examples like this problem that we didn't have time to do more of in class. Come to my office hours. That's a perfect time for us to do some extra problems together. We can hang out. It's not going to be like a whole thing. You can just show up and we'll do a couple problems. I can help you with your homework. If you have questions on the homework, come to the office hours. It's a useful thing. Okay, that's all for today.
Waiting for Monday class.
Monday, thank you for asking. Monday class is remote, okay? So what I'm going to do is lecture like I'm lecturing now, except I'm going to do it at home and record it and post it on YouTube, and you can watch it whenever you want, okay? So you'll have to basically just watch the YouTube video. That's what you have to do for Monday's class. Thank you for asking that.